So that he will be giving 3 lectures. I'll be gone for 3 lectures all of next week, and the lab is covered. Cindy and Lucy will do the AA, and then I invited Kati to help with the MS along with Rachel. Myson also will be in Europe as well. So, and then the test is going to be the Monday after next week, so on the 29th. So I will come back and ready to give you a test. But the test will be all the way up to the end of this week, so last Friday lecture. So the Buza's lectures will not be on that exam, okay? So all the way to this Friday's lecture, okay? One of the HPLC lectures I gave did not record well, but I have last year's sort of similar lecture, so I posted that on Canvas. Okay. Guess this is all I have. All right, so spectroscopy. This is another fascinating topic. Chromatography and spectroscopy are the most important analytical tools in analysis. So everything is going to be everything we're going to analyze or work with will have an element of spectroscopy in it. Almost everything. So it's a very important tool, and that's why we're going to go over principles. Some of this principle requires you to remember some of your physics, which I'm not a fan of physics, and I'm sure many of you are not fans of physics, but we will have to swallow and take it with a grain of salt a little bit, review the principle that will help us understand the tools and the applications in food analysis. Okay, let's remember a little bit about the physics of light that you know. So the following are associated with a light wave: electric field, magnetic field, and photons. Which of these you can think of are related to light? I appreciate Evan's courage in answering this question. It is partially correct. So you don't like magnetic field, do you? No. Doesn't feel right. Hold on, Sam. Nick?
What if photons be affected by magnetic field?
You're being very creative, Sam.
Yeah, I mean, I was just gonna, I'm just spitballing here. Like, I think of like light coming from the sun and like the magnetic field around like Earth stopping some. That might just be radiation, actually, not light. I don't know. I'm just throwing something out there.
You know, if I put your answer and Nick's and Daniel and Evan together, we actually have an answer. All of this. So if you think of light as a wave, it's actually an oscillating fields of electric and magnetic field together. So it's called electromagnetic field. Light is the electromagnetic radiation. Light is basically electromagnetic radiation. And the light has a wave characteristic, electromagnetic characteristics, and they have a particulate characteristics. So if you think of light as a particulate of energy, then you think of photons. So light have a particulate characteristic and it have a wave characteristic. And then we will go into that more in detail. So following spectroscopy as means of analysis, detection can be based on. We did spectroscopy in caffeine lab. We measured UV absorption. But absorption is not the only measure for spectroscopy. So which of these could be correct? I know you know. Riley. All of the above. So we can measure absorption, we can measure emission, we can measure dissipation. We all agree? Sam?
I would say maybe not emission, only because a lot of like they're not necessarily like emitting photons unless it's actually like a light source. It might be like reflecting it, but I don't know if that counts as emission.
Okay, any other opinion? Hold that thought. Any other opinion? Come on, just discussion. It's okay if we don't get it right. We're just talking. Yes. You are absolutely right. It's A and B. So we measure absorption. That's regular absorption spectroscopy. We can measure emission, and that's fluorescence. So when you're measuring fluorescence, you're actually measuring the emission of light or photons of light after going from excited state to ground state. Because when a molecule or an atom absorbs energy or light, it goes to an excited state. But it doesn't stay there. It just stays there for a little bit, few seconds or less. Then it wants to go back. When it goes back, it's moving, so it dissipates some heat. But the heat, the increment of heat is too small, we cannot measure it. So we cannot use measurement of heat to determine a quantity or to identify. It's just too small to be detected. But we can, if it emits a photon, then we can measure fluorescence. So the photon of emission, it has less energy than the photon of absorption. Why? Because part of the energy was emitted as heat. Some energy was lost as heat by just vibrating and moving. So part of the energy goes out at heat. Part of the energy is emitted as a photon. So this photon carries less energy than the original photon that was absorbed. So these are important to remember, these concepts for later. Okay. So what is spectroscopy? It's really a study of the interactions of electromagnetic radiation with matter. So whenever you have the light interacting with matter, you have spectroscopy going on. So spectroscopy is dependent on the species. So you either have molecule absorbing light or interacting with light, or you have atoms, like the group that did atomic absorption today in lab. It was all about breaking the molecules into atoms and determine the absorption of the atom in a gaseous state. So so spectroscopy can be for molecules or atoms, and the interaction can be in the form of measuring absorption of light, emission of light, scattering of light, or diffraction of light. So that all of these different interaction gives us a unique tool for analysis. Either we're measuring absorption, or we're measuring emission, or we're measuring light scattering, or we are actually using diffraction to do the analysis, and I will explain that in a minute. Another important thing is the electromagnetic region. So that means the wavelength at which we are monitoring the interaction with the matter. So you have radiation that ranges from radio radiation, microwave, infrared, visible, UV, X-ray, gamma rays. So this is the longest, the radio is the longest, and the gamma rays are the shortest. And the shorter the wave is, the highest is the energy that it carries. And I'll explain that in a minute. It depends on how many oscillations per unit time. And I'll explain that in a minute. So absorption can occur. In food analysis, this region that is important. Infrared, visible, and UV. These are the most important regions in analysis. So spectroscopy generates a spectra, generates data that we can use to detect, to quantitate, etc. So we have UV vis absorption. We did UV absorption for the caffeine lab, for example. Infrared, we're going to talk about it later this week. So infrared, and we use it also in many different applications in food analysis. Fluorescence, and then atomic absorption. We will talk that, I think, on Friday. We'll get to that. And then also we're going to talk about inductively coupled plasma emission, which is unique for elemental analysis, but it measures fluorescence, emission of light in this case. Nuclear magnetic resonance is another form of spectroscopy, but we will not cover it in this class. And mass spectrometry is provide a spectra, but has nothing to do with light in particular. But it is, usually they're bulked together. Spectroscopy is spectrometry, bulked together. So what types of application do you think we can use spectroscopy and spectrometry? What types of application in food analysis? Lauren? Quantification. One of it is determining mineral content. Yes, quantification. What else?
Like identification, because it has like a ring of reflected light.
Absolutely, identification. When we don't know what compounds we have, we look at its spectra, we can potentially identify it. So quantification, identification, quantification, identification, qualitative detection, just to determine the presence of. Composition and analysis, this is very, if you hear NIR instrument, mid-IR instrument, you use them to determine. Mid-IR is commonly used for milk composition. Near-IR is very common for composition of different food components. They are secondary methods of analysis, and we'll talk about them as well. If not this week, when I come back. Quality assurance and forensic spectroscopy is often used to look for things in food that we don't know. So we use spectroscopy to identify the presence of a foreign matter, to determine the quality, to ensure quality of the product. And of course for structural elucidation, like FTIR, for example, NMR. FTIR is commonly used to determine structural based on the bonding of the different functional groups. So we'll talk about that when we cover IR in more detail. So there are a wide range of applications and categories of applications for spectroscopy. And in this class, you will encounter spectroscopy numerous times. HPLC, you encountered it with the caffeine, you will encounter it with the mineral analysis, with carbohydrate analysis, with several other labs. Okay, let's step back and remember our wave characteristics or wave-like properties of light. So here is a light wave. So it's basically the oscillation of electric and magnetic field. And with that, let's learn certain parameters that will come up quite often. So you have lambda, which is a wavelength. And it's really the distance between two maxima of a repeated oscillation. So the maxima here and the maxima here, and distance between them is your wavelength. So the frequency is how many oscillations you have within a unit time. So the number of occurrences of a repeated event. So from highest to minimum, that's a repeated event, and it repeats itself. Okay? So the shorter the wavelength, the more oscillations you're going to get in a certain period of time, and that's why you have higher energy with shorter wavelength. You have more frequency, and we'll see the equation later with energy related to frequency. Amplitude is basically the magnitude of the electric vector at the wave maxima. So these are common parameters. So wave-like properties, we have interference, diffraction, and refraction. So if we talk about interference, this will come back again when we talk about IR and FTIR, Fourier transfer infrared. So in that instrument, we're going to talk about how the mechanics of that instrument uses interference of light. So what does that mean? So if you have two wavelengths passing together in space, and they overlap where both maxima overlap and minima overlap, you get amplification of that wavelength. And that is commonly used to enhance sensitivity in IR instrumentation. Another form of interference, if they were out of phase, that means if one wavelength interferes with another, but the maxima is at the minima of the other one, and vice versa, you get cancellation. You lose the energy completely. Diffraction, this is very common tool we use in spectroscopy where the light gets hit a diffracting system or diffraction grating system. Sometimes it's a prism, and the light gets diffracted into individual wavelengths or waves of individual length. This is important when we want to determine absorption at a particular wavelength. So we need to select the wavelength at which we measure absorption. We diffract the light into the individual wavelengths. Refraction of light, which is common in refractive index, for example, and that's when the angle, when the light hits at a certain angle of incidence in first medium. However, when it travels into a second medium, it diffracts or refracts. It changes direction, and you have an angle of refraction. Okay? That's the principle behind measuring refractive index, how much the light refracted or changed direction. In analysis, we tend to refer to light as a photon of light, using its particulate properties. So a wave consists of discrete pockets of energy, and we call them photons. The energy of a photon is directly related to the frequency, which is number of oscillation per unit time. And the H is a constant. So the higher the frequency, the higher is the energy of the photon. So let's talk about parameters you will encounter as well, such as monochromatic light. I think we talked about it a little bit last time. Do you remember what a monochromatic light is? Mono, one, wavelength. So the light that is at the particular wavelength. So it's electromagnetic radiation composed of waves having a single frequency and wavelength. That's the complete definition of monochromatic light. And having a single frequency, that means they have equivalent energy. So monochromators are used a lot in spectroscopy. So what they are is they are a unit within a spectrophotometer where the light gets diffracted. So here's an incident of light. I don't know, I need to change the battery of this. Here's the incident of light. It hits a mirror and then gets reflected onto a grating system that diffracts the light into multiple wavelengths. And then you have here an outlet which has a slit that allows a single wave, a light wave, got stumbled here, a light wave at a single wavelength that passes through, hits a mirror and gets reflected potentially here to a sample, where a sample absorbed as a single wavelength. You can also have a crystal that would cause also diffraction of light. A photon flux is the number of photons flowing across a unit area, perpendicular to the beam. So here's the beam, here's the unit area. So how many photons are hitting that area is basically what it is per unit time. Brightness or radiant intensity is basically the energy that hits a unit area per unit time. And brightness is often adjusted to get optimum absorption or optimum fluorescence, whatever we're measuring, and enhancing the sensitivity. Okay. I'm going to skip the recap questions for now. We'll get back to them. So again, we have different waves, different lengths of waves, and as the wavelength gets smaller, we have higher frequency, higher energy. So this way the energy is higher. And also, like I said, the most important region, we have the ultraviolet for analysis, we have the visible light, and the infrared radiation. This region is most important for analysis. So the particulate property, so the photons is either absorbed or emitted. So, and that's what we measure, absorption or emission of photons of light. So you have ground state, and then a photon hits an atom or an electron on an atom, a valence electron. That electron is going to go to a higher orbit or a higher shell. So it will carry, the atom in the excited state is going to carry the energy equivalent to the energy of the photon that struck it. So that is, we call absorption of light. When an electron jumps from ground state to an excited state, a lower shell to a higher shell, it's absorbing the light or the photon of light. However, it doesn't stay in the excited state, goes down to the ground state. So the electron is going to go from a higher orbit back to its original orbit, but in the meantime is going to dissipate some heat, and the remainder of the energy is going to be emitted as a photon of light. But this photon carries higher energy than this photon here, because some of the energy was lost as heat. So which one will have longer wavelength? This photon that struck or the photon that is released? Marissa? The photon that is being released will have less energy because some of that energy has been lost. Accordingly, it has a longer wavelength. So that's important to remember, that the emitted light has longer wavelength than the absorbed light. So Under certain conditions, a molecule struck by a photon may absorb the photon's energy. And I say may, not always, because the energy has to match the allowable potential energy that the atom or molecule can absorb. That's why some molecules absorb at different wavelengths. Because if the energy that hits them is not within the allowable potential energy of these atoms or molecules, they will not absorb light at that particular wavelength. So that's why they say here may. So when a photon hits a molecule, it may absorb that energy. And if it absorbs it, it goes from ground state to excited state. And the change in energy is equal to the energy of the photon. That's why it's equal HV, the same unit. The change in energy of the atom or the molecule will be equivalent to the energy of the photon that hits it. So the internal energy content of a molecule does vary in a series of discrete steps and not in a continuous manner. So that means there are discrete levels of energy that are not necessarily continuous. And every atom or molecule have a unique discrete steps of potential energy that they can change from one level to the other. So here they are, those discrete steps. So there is a whole set of available energy level for a given atom or molecule. Those levels are unique for each species of molecule. So this is, for example, an illustration of E0, that means at the ground state. And when that atom or molecule get hit, it might go to a higher level of energy or even another higher level. So it can go from 0 to 1 to 2. Only is if the photon carries energy within its allowable potential energy. This is really important to know that this is unique, that the energy within this compartment here and this compartment, this level is unique for each molecule or atom. If the photon that hits the atom or the molecule does not carry the energy that is equivalent to these steps, to these levels, then there is no absorption. The different types of energy are electronic, vibrational, and rotational. So you can get electronic energy or increase in vibrational energy, which are smaller units than the electronic energy, or you can absorb energy that gives rotational energy. And here they are. So if we look at electronic, from its name, it's the energy that results in the electron moving to a higher shell. So that is a transition between orbits. So electrons in each orbit and each level have different potential energy. So that's why it depends on how much energy gets hit or strike the atom. It depends how much energy each electron has the potential to go to an upper and more excited state. So change in the potential energy of an electron will lead to change in the potential energy of the atom or a molecule. So the electron could be only in a singular atom, or it could be in an atom that is within a molecule. So it could be valence electron or electrons in a bond. So the electrons that move to an excited state could be electrons in a singular atom, or they could be the valence electron of an atom within a molecule, or the electrons that are participating in a bond. I'm just repeating that. So the magnitude of energy difference between the ground state and the excited states for valence electrons and bonding electrons of a molecule is of the same range as the energy of photons of the UV vis radiation. So in that range, in the UV vis radiation, you get change in electronic energy. Okay. So vibrational energy, so this is very specific to molecules only, not atoms. Vibration is the vibrations of atoms within a molecule that are bonded together. So molecules forming atoms are in constant motion, vibrating in many ways, and we will cover that when I cover the IR lecture. So each bond is vibrating, is always in constant vibrating, either stretching or bending. So that vibration is a vibrational energy. It's associated with IR radiation. In this case, the allowable energy is within the range of the IR radiation. So V1, V2, V3, these are corresponding to the vibrational energies, and they are smaller than electronic energy. That's why they are overlapping within each energy level, each electronic energy level. Like I said, these are equivalent to IR radiation. So the distances of vibrational energy allowable is equivalent to the energy that is carried by the photons in the IR radiation. Rotational energy is the rotation of the molecule around its central or center of gravity. This is equivalent to radiation within the microwave range and is not of interest for the NASA. We do not use the rotational energy in terms of detection. So there is no tool that we use for detection and quantification in this range. And the rotational energies are smaller, the levels are smaller than vibrational and smaller than electronic. So the energy of an atom is equal to the energy of the electronic energy, whereas the energy of a molecule is equal to electronic plus vibrational plus rotational. So each of the associated energies is quantized. Like I said, they're not continuous scale, and they're very unique and different for each species. And that's how we differentiate and use this tool to identify and do structural elucidation. So here's an example of a spectrum. So I'm going to draw a couple other spectrum just to illustrate the point that absorption only occurs when the energy is equivalent to the allowable energy transferred within the molecule or the atom. So if we have two molecules, so one has a maxima, let's say, at 280, and another one absorbed at 320, let's say. So that's lambda, that's lambda. So basically, in order for this compound X and Y, in order for this compound X to absorb light, we need to hit it with an energy level equivalent to lambda 280. I mean, it can absorb at 260, it can absorb at 290, but really, in order for it to move from E0 to E1 or potentially E2, this distance, these distances should be equivalent to the energy provided by this wavelength. Whereas this one, if we hit this Y with 280, there is no absorption. So there is no change from E0 to E2, E1. These are probably different. So this is X, this is Y. So the distance between E0 to E1 could be different. It requires higher energy, or maybe in this case lower energy, because it's larger lambda. So it requires shorter distance, I mean lower energy, so you need longer wavelength for it to absorb and move to higher energy level. So that's why we have a spectrum that is unique for potentially every molecule, because it is dependent on their energy levels and allowable energy levels. So emission spectroscopy, so in this case, it is basically the fluorescence. So excited state typically remains only for a very short period of time, and then it relaxes. So we said it goes from an excited state back to ground state, and it emits a photon that is of a longer wavelength, and that becomes, that is what we call fluorescence. When emission of light is fluorescence. So dissipating of energy can be in the form of releasing heat as well as releasing a photon of light. Ah, that's it. I finished early. Do you have any questions? Wow. Can start a new topic. Unless you have questions. I didn't expect that we finished very early. Let me see. Either you have questions or I'm going to start a new lecture. Zach doesn't want me to start a new lecture.
Well, do you want to go through the recap questions that you skipped over?
Oh, that's a good idea. Smart. Do you have that or you don't? It's not in the... Okay. What are the different species of matter that can be analyzed using spectroscopy? Don't look back. Let's see how much you learned. Oh, you learned nothing. What? Yes. Atoms and molecules, yes. So an example of atoms is the atomic absorption spectroscopy, where we determine the content of minerals in their atomic state, in the gaseous form. And then molecules is like when we determine caffeine. It's a molecule. We determine the absorption of caffeine or the UV absorption of caffeine. So species are either atoms or molecules. Name the different forms of radiation-matter interactions. What did we talk about in terms of interactions? How can they interact?
Well, the electronic, vibrational energy.
These are the different types of energy. But what forms of interactions there are between radiation and matter? Grace. There's a refraction. absorption, emission, and diffraction of light. So a matter can diffract light, can scatter light, can refract light, can absorb light, and can emit light. What are the spectral regions most relevant to food analysis? Axel?
Ultraviolet, infrared, visible.
Yes. Ultraviolet, visible, and infrared. Which of these three has the highest, longest wavelengths? Ali? IR. Okay. And it carries the least energy. What's the difference between electronic and vibrational energy, and to what spectral region each corresponds to? Let's answer the first one. What's the difference between electronic and vibrational energy? Electronic energy is energy of what? What's in the atom that changes energy? From the name. The electrons. So the electrons are going to jump to a higher shell or orbit once they are struck with a photon that is within their allowable energy or changes in energy. What's vibrational energy?
The energy of molecules depending on how it's vibrating.
How the atoms are vibrating within the molecule. Okay, so electronic energy corresponds to which spectral region? UV, vis, infrared. Electronic corresponds to the energy carried by UV visible light. So UV visible energy allows for electronic transition, because in the UV visible light you have higher energy, and remember the energy levels of the electronic is larger than the energy level of the vibration, and the vibrational energy is lower because you have longer wavelength for IR, and IR is the spectral region for vibrational energy. Because IR is the spectral region for vibrational energy, it carries less energy with it. Therefore, changes in vibrational energy is less than changes in the size of the electronic energy. What's the difference between absorption and fluorescence? Yes, exactly. So a little bit is less as heat. So emission is of a photon of a lower energy, and that is the fluorescence. Okay, what's the difference between diffraction and refraction of light? What's the diffraction of light? Yes, Axel? Yes, so when light is diffracted into individual wavelengths by using a prism or a grating surface. Whereas refraction of light is when the light changes direction as it hits a different medium. It gets refracted. How does the wavelength impact the frequency and energy? We talked about that as we answered this. So the longer the wavelength, the lower is the frequency and the lower is the energy. Whereas the shorter of the wavelength, that means you have more oscillations within a unit time. That means you have higher frequency, and with higher frequency you have higher energy. Okay, well, Zach saved you all from a new topic today.